Hey, let's talk about tree-based signatures. We'll first start by taking a closer look at these chain-based signatures and what happened there. In chain-based signatures, we had one key in the beginning, the PK1, and then essentially we've used this key to authenticate a new public key, PK2. Authenticated in the sense that under PK1 we created a signature sigma1, and that signature signed the message PK2. It also signed a message M, but that's not too important for us right now. And then PK2 went along to authenticate a new public key PK3, and it authenticated that by having a signature sigma2 valid under PK2 on PK3. So in the end, if someone saw this chain of signatures and they were aware of the first public key, PK1, then they could iteratively check whether all of the public keys are valid successors of this one public key. So essentially our public key is just this one public key on the top, this root public key. And then in each step we added one new public key, which we authenticated by using the public key before it. And then essentially you can trust PK3 because you have a signature under PK2. And you can trust PK2 because you have a signature under PK1. Okay, and then through this chain, you essentially, as soon as you get to PK1 and indirectly PK1 has signed PK3 by first signing PK2 and then PK2 signed PK3, we have this chain of trust essentially. Now for tree-based signatures, something very similar happens. We still have a root key, call this PK epsilon here. But now the idea is that we don't only sign one public key, but we sign two public keys. So essentially, again, everyone knows PK epsilon. And if you give me PK0 and the signature on PK0 under PK epsilon, then I can easily check that this is also like one of your public keys. Note that technically for this check you also need to give me PK1 because I need to call the verify algorithm with the complete message that was signed by this signature, but never mind for now. And now we can extend this thing. So then PK0 can, for example, again, sign two new public keys. And PK12 can do the same. So then if you wanted to prove to me that PK01 is actually one of the public keys that belongs to you, what you can do is you can give me sigma0, which is the signature on PK01, under PK0. And then how can I trust PK0? Well, you give me sigma epsilon, which is a signature on PK0 under PK epsilon. And I trust PK epsilon. So why is this cool? Well, in contrast to the chain-based signatures, where we only had one public key per iteration, now in this data structure here, we can very easily get to very many levels. So in the end, if we have like a tree of depth n here, then we have 2 to the n public keys that we can authenticate using this chain idea. And then this thing plays nicely with one-time signatures. So if I can very easily get a huge bunch of public keys that I can use, then I can easily say, okay, let's just have one public key specifically designed for one particular message. So this public key here is destined to only sign this one message, which is 00. This public key here is destined to only sign the message 10. And then this is kind of nice for a one-time signature scheme because each one-time signature key must only be used once for this one message. And then the trick to make this an actual stateful signature scheme is to not construct this whole tree at once, but to basically only construct the parts of the trees that are now immediately necessary. So we can't construct the whole tree at once because, well, even only on this level, there are 2 to the n public keys that we would have to come up with. And, well, this is just too much. We can't just generate 2 to the n keys in polynomial time. So what we do instead is say we wanted to sign the message 01 then what we do is we generate this public key, and then we generate all of the keys on the way to the root, and also the signatures on the way to the root that we need in order to authenticate this public key PK01. And then we just store this part of the tree in our state. So this is exactly what's going on in this construction too. We have one public key secret key pair that's destined to sign one particular message. And then this part generates all of the keys in the tree that we need in order to authenticate this public key for that message, if they have not been generated by a previous run through the signature scheme. And then verify will basically check each of the signatures that authenticate the public keys on the way down to the one public key that signs the message. And then it will check the signature on the message. So let's play through an example. Let's say we want to sign the message 1011. And we haven't signed anything before. The only thing that is known is the key pair sk epsilon pk epsilon and nothing else. This is what we get from the key generation algorithm. So ultimately, in order to sign this message, we will generate a new key pair for that message because we haven't generated this before. And then we will generate all of the stuff that we need in the tree in order to authenticate that public key PK1011. And what actually is this? So what parts of the trees do we need to generate now? Think about it for a second, then I will mark the solution. Okay, so whenever I mark a node green, this means that we will have to generate and store the public key secret key pair for it. So this is this leaf node here, which is exactly the 1011 node. So 1011. That's definitely something we generate because this is what we sign the message from. Then in order to authenticate that node, we will have to generate the keys for the parent node. And remember this node here, the parent node, the key of this will be used to generate a signature to authenticate both its children. So if I want to generate the signature, I also need to generate the other child's public key. So then to authenticate the 101 node, this one, we will have to generate a key for this node. So again, the key for this node is used to authenticate its two children nodes, so the public keys of its two children. So in order to make this work, I also need to generate the public key of this 100 node. Good, and then this goes on. So again, we need to generate this key pair to authenticate the 10 node. Then in order for this to work, we also need to have its sibling to generate the signature. And then we go to the top. That node we already have the public key. And both of the children need to be generated too. So this means in order to generate this one signature here, in order to authenticate the public key for it, we generated on each level 2 keys. So these two, these two, these two, these two, and then, well, this one we already had. And this immediately gives us this idea that runtime-wise this kind of works. We need to do some 2 things per level of this tree. There are n levels, so just 2 n operations of generating keys. And maybe we even have some keys already in our state, then we don't even need to do a new key generation for those. So runtime-wise, this works. And then the signature on our 1011 contains all of the stuff to check this whole chain of public keys. So it contains this signature that signs these 2 public keys. It contains this signature that contains both these public keys. Then it contains the signature that belongs here, and then finally the signature here. And obviously to verify the signature, you also need to know the message that is signed in the signature. So all of these public keys that are currently marked in green here, they also need to be published alongside the message. So then let's say we sign an additional message afterwards. let's say 1110. So which nodes will have to be generated new now? Right, so the one node for which we want to generate the signature. The key for this needs to be generated, and then also its parent, and it's all of the children of the parent. So the key pair for this parent node is already generated, but now we need to create the signature that authenticates both the children, which we didn't have previously because we only generated the public key when we needed to generate the signature on these two. So now we add this. So we generate this key, the 110 key, and then sign these two public keys here. And then all the other nodes are already generated. So if we look at the signature on 1011, it looks as follows. So in each level we get a signature. At the end we get the signature on 1011, which is the one that we wanted. And this thing is under the public key PK1011. Now this public key PK1011 is authenticated by Sigma 101, and that Sigma 101 is under public key PK101. Then this public key again is authenticated by Sigma 10, which is valid under public key 10, which is authenticated by Sigma 1, which is valid under PK1, which is signed by Sigma epsilon. And Sigma epsilon is valid under PK epsilon, which is just our public key. So similar to chain-based signatures, we had this chain of this public key authenticates this next public key, etc. Now only it also authenticates like its sibling public key too, but it doesn't actually matter to us too much. So just to make the next part a bit easier, I'll mark in the tree which signatures we've actually revealed in this scenario where we have signed 1011 and 1110. So this blue thing here means that we have released Sigma 1 to the public, essentially as part of some signature, and we've also stored it in our state. So the security proof of this is also kind of similar to the one that we had for chain-based signatures, meaning that we start with an adversary against this tree-based scheme, and we construct an adversary against the one-time signature scheme. Now the adversary against the one-time signature scheme, so the adversary that we're constructing, it will get a public key pk star as input. And its goal is to forge a signature under this. Essentially all of the other public key secret keys, it will generate honestly, but it will guess some sort of position I star such that pk I star is pk star. So again, we're guessing a position in this tree where we smuggle in our pk star. Now we need to be careful because we can't just choose I star as a uniformly random position in this tree, because there are way too many positions in this tree. And because there are way too many, because there are more than 2 to the n positions in this tree, us guessing correctly essentially is just 2 to the minus n probability, or even less. And that's too little. Like if we only guess correctly with a negligible probability, then we haven't gained anything. We can also just try guessing the key. So what we can do instead is we have an upper bound on the number of keys that we generate during this experiment. Because the adversary only makes polynomially many queries, in each query we only generate at most 2 times n key pairs. So overall we only have polynomially many key pairs that we generate. Let's say at most q of n. And then actually we guess like an index j star, and then we just generate I star to be the position in the tree for which we generate the j starth key. So we generate at most q of n keys. We guess which of these key generations we will want to smuggle our PK star into. And then we just, let's say I star now is the position of the tree where this happened, where we've smuggled in our PK star. So now we have only guessed among polynomially many possibilities and not among exponentially many possibilities. So now we are fine again. So now let's say the A prime that we are constructing now runs A internally, and it just answers signatures queries as it would usually do. If it needed to use PK star, then it will ask for the challenger for the signature. And then eventually we will have such a state. Just we won't know the secret key for PK star, so this is not actually part of the state, but all of this other stuff is there. And let's say for this example that actually the adversary has queried these two signatures. So for 1011 and for 1110. So that the picture of the tree that we have here in our state is actually accurate. So now let's say the adversary has output a forgery on, let's say, 0010, just as an example. And then this forgery looks as follows. And I'll mark the stuff we got from him in the tree. So what do we know? We know that this signature here we have never generated. So we have never generated a signature on 0010. So we definitely know that this is not part of our state and that we have never created this thing. We also know that the signature is valid under PK0010 prime. So some public key that the adversary gave to us, we don't necessarily know what it is. But we know that whatever public key this PK prime 0010 is, it's authenticated by sigma 001 prime, and that is a signature under the public key PK001 prime, and etc. Until eventually sigma epsilon prime needs to be a valid signature under PK epsilon. That's what the verify algorithm has to make sure. Now, similarly to the chain-based signatures, now there needs to be some index in this chain of things here, where there's the first deviation from what our tree would have said. So for example, if we had already generated PK0, PK1, then the adversary may or may not output the same public keys. Let's say in this case he did. So let's say those are the same keys that we have in our tree. So in this example, already the next position deviates from our state because we have never generated a signature on 00 or 01. So for these nodes, we have never generated a signature, which means that in this case, while sigma epsilon prime is not a forgery because it's a signature on PK0, PK1, the same that we already generated. However, the next one is a valid signature under PK0 on a message that we have never signed. So there we have our signature forgery. It could have also happened that here on the first level already, this is not equal to PK0, PK1. So then already sigma epsilon prime would have been a forgery. Because in our game, for the signature key, we have only generated a signature on PK0, PK1 under PK epsilon. And clearly, in this case, we would have gotten a different message. So essentially, there needs to be some index in this chain where it first deviates from our state. Okay, it cannot be completely in our state because, as we noted, this is we have never generated this. So in the worst case, kind of at the last signature, we get this deviation from our state. And whenever we get a deviation from our state, we get a forgery. Because then we get a signature on something that we have never signed. So until this index I, everything is still the same as in our state. In particular, all of the signed public keys are the same. And then at position I, which will now be a valid signature under one of the public keys on the level above, which, remember, is still one of the public keys that is part of our state. That signature now signs something different, but it did it with one of our public keys. So there we get our forgery. And then we just need to be lucky that I star is equal to I. And then if we are lucky, we get our forgery and everything is fine. But the formal analysis is not all that interesting here. The important part you need to be able to answer in the exam is actually if you get such a forgery, like here, you need to be able to argue that somewhere in this forgery, for the tree-based scheme, there is some forgery for one-time signature scheme. And then again, you get this by looking at this forgery level by level and searching for the first level where something deviates from your state. Then on that level that deviates from your state, you have a signature that is under a public key that is from a previous level. So it's one of the levels where the public key is in your state. And if we're lucky, then it's actually the one that we smuggled into the state. And on this level, it deviates, so it signs a different message. And then this is our forgery. Okay, that's it for tree-based signatures. Thank you for listening and see you.